So is light a wave or a particle? We've probably always thought of light as being a wave, but based on what we saw with the photoelectric effect, it also seems to behave as a particle. And this is where Einstein's idea of wave-particle duality comes in, or the dual nature of light. Depending on the situation, light can behave as both a wave and a particle. And so, looking at our equation from last time, our photon of light can have an energy that's given by E equals hf. Here, E is the energy of the photon, h is Planck's constant, which remember is that very, very small number, 6.63 times 10 to the negative 34th. F is the frequency of the wavelength in cycles per second. But if we're really going to consider light a particle, we have to consider its momentum, because moving particles have momentum. And the equation for momentum is given by mass times velocity. So P, which is momentum, is equal to the mass of the particle, m, times its velocity, times its speed in meters per second. So mass is given always in kilograms. V is in meters per second. And so then momentum, the units for momentum are just kilograms times meters per second. There's no derived unit for this like the Newton. It's just left in kilogram meters per second. Now, also according to Einstein, the energy of a particle, the energy associated with a particle, is equal to mc squared, the mass of the particle times the speed of light squared. Well, if we rearrange that to solve for mass, the mass then is equal to that energy divided by the speed of light squared. So m equals E over c squared. We can take that expression for mass, E over c squared, and plug it back into our momentum equation. And so if we do that, we get the momentum is equal to E over c squared times c, because remember, P equals mass times velocity. If the particle we're talking about is light, light travels at the speed of light, which is c. And so our speed of light on the top cancels out. We can lose one of the c's that's at the bottom. And so we get the momentum is equal to E divided by c. The momentum of the particle is equal to the energy of the particle divided by the speed of light. Well, remember that from up top, from Einstein's equation, E is equal to hf. And so we can plug that in for the energy here. And so we get the momentum is equal to frequency divided by c, by speed of light. Our wave equation relates speed, frequency, and wavelength. And so it's v equals f lambda. And in this case, we're talking about waves. We're talking about electromagnetic radiation or electromagnetic waves. And here we have frequency over speed, so f over v essentially. And so if we rearrange our v equals f lambda and we solve for f over v ends up being 1 over lambda. And so if we plug 1 over lambda in for f over v, we get the momentum of a particle of light equal to Planck's constant divided by the wavelength of light. So P equals h over lambda. Mathematically, we can show that light should be able to behave as either a wave or a particle, depending on the equation we use. But you have to be able to back that up experimentally. And the photoelectric effect and all of the experimentation done on the photoelectric effect is evidence for the fact that light can act as a particle. But we also have to show that it can behave as a wave, and that's done through Young's double slit experiment. Young's double slit experiment, basically you have light shining through two very thin slits that are very close together, and as the waves travel through, they are diffracted, and you get a diffraction pattern, which are areas of light and dark. And that effect from the double slit experiment is evidence of interference, both constructive and destructive, which is evidence in support of light behaving as a wave. So even though light can behave as a particle, it also has wave-like properties. And this is our wave-particle duality. Now that's well and good for electromagnetic radiation, but in 1923, Louis de Broglie said, well, if light can behave as particles, then why can't particles behave as waves or have wave properties associated with them? And so he proposed the idea of the wave-particle duality of matter. And he kind of looked at it from a different perspective. He said that if all waves have momentum, then all things that have momentum should have an associated wavelength. And he drew this conclusion initially in just a very simple mathematical way, because Einstein had said that the momentum of any wavelength was equal to Planck's constant divided by its wavelength. And if this was true, then we could rearrange the equation to solve for wavelength, and there we would get lambda equals h over p, or Planck's constant over momentum, which we can also then substitute in mv for momentum and see that theoretically anything that has mass and velocity, momentum, should have some associated wavelength. And that was the reasoning that de Broglie followed. Now looking at this equation, lambda equals h over p, we can see that as the momentum of the particle increases, and most commonly that's through an increase in mass, the wavelength is going to decrease. And keeping in mind the very small nature of Planck's constant, remember it's 10 to the negative 34th in power, anything that has any type of significant mass is going to have an incredibly small wavelength, even unmeasurable. But if we get something very, very small, something say like an electron, that might have a wavelength that's measurable. And so just like anything, any type of theory, if you're going to present a theory, it helps if you can support it with evidence. So if we look at the numbers associated with an electron, it has a mass of about 9.1 times 10 to the negative 31 kilograms, so very, very small. It moves with an average speed of about 10 to the 5th meters per second. And so our momentum, we're looking somewhere around 9.1 times 10 to the negative 26th. So very, very small momentum, and something that could potentially have a measurable wavelength. If we plug that into our lambda equals h over p, we get the wavelength of an electron, the theoretical wavelength associated with an electron, to be 7.2 times 10 to the negative 9 meters. Okay, so certainly something that should be measurable. If we're going to apply wave physics to this, and we're going to try and look at diffraction patterns, then to get an opening that would provide enough diffraction, we would have to have something that's in the order of 10 to the negative 8 meters in size. And when we're talking about that size, we're at the crystal structure level. We're down so small that we're talking about distances between atoms in crystals. And so, way then theoretically to support the existence of wave properties of matter would be to pass a beam of electrons in between the atoms in a crystal lattice and observe whether or not diffraction occurred. Electrons are small enough that they should pass through that distance with no change in their trajectory. So if electrons didn't have any wave nature, They were just particles. It was very straightforward. They should pass through, and there should be a single spot on the surface down here where all of the electrons are hitting. However, when an experiment similar to this was actually done, what scientists found was that there was a diffraction pattern. There was a pattern that occurred where we had areas of a lot of electrons hitting and areas where there were very few electrons hitting, which corresponded to maximas and minimas that would come from a light diffraction pattern. And when they used the distance between those maxima and minimas and calculated them backwards, they got a wavelength that would be associated with it that was very, very close to what was theorized should be the wavelength of an electron. Now, in 1927, Clinton Davison and Lester Germer were designing and performing an experiment in which they were actually trying to study the surface of nickel crystal. And their intention was to shine a beam of electrons on the nickel crystal and measure the deflection of the beam of electrons off of it to get a better sense of what the surface of the nickel crystal looked like. What they actually did was provide the first solid evidence in support of the de Broglie theory that matter acted as particles in waves. You can see the setup here just in a really basic diagram. Essentially what they had was a beam of electrons coming out of the spot A here, passing through an opening and then striking the surface of nickel crystal that was at some angle. Then they had a detector that moved around the outside and was able to measure the number of electrons that were passing through that point. And what they actually found was that as they moved around at different angles, there were maxima and minimas. Just as we talked about a few moments ago, there was basically a diffraction pattern occurring when the electrons were being reflected off of the surface of the nickel. And so this data was the first real evidence that supported de Broglie, and thus supported the theory that not only does electromagnetic radiation have both wave natures and particle natures, but matter can also have wave natures and particle nature, and so it brought together this whole wave-particle duality idea.